So this is where we left off. And we were talking about the problem that the structure of benzene started to give chemists way back in the early days. So we thought that we got this idea of benzene structure. We thought that we had it down. 6 carbons, 6 hydrogens, and you see that structure over on the left-hand side. The problem is that it has double bond characteristic. And that double bond, because I've told you all along, if there's a double bond there, it's going to react. But benzene never really did react like normal traditional alkenes did with all of those alkene reactions. So it was almost like on a sheet of paper it was an alkene, but then when you look at it face value, folks, it had no characteristic like an alkene at all. How could this actually be? Well, before I tell you that, I want to talk to you about a man named Kekulé. Here's Kekulé over onto the right-hand side. And Mr. Kekulé, you can kind of thank for the Kekulé structures that we've been talking about, that we've been drawing throughout this class. And I really don't know what he was smoking. I don't really know what he was on or what he was taking. I mean, that was kind of common back in the day, actually. It's before a drug was labeled as a drug and people just did whatever they wanted to do, it seemed like. But he said that he fell asleep at the fireplace. And he had a dream. It was more like a psychedelic dream. And what he dreamed of snakes and dragons making circles, biting their tails. And then he woke up and he said, "Eureka, I've got the structure of benzene." Could you imagine? Could you imagine telling that to somebody? They would have you probably committed to some kind of psychiatric institution at today's environment. But this psychedelic kind of crazy dream that Kekulé had by his fireplace, and again, who knows what he was on, led to the discovery of the benzene structure and these ring structures that could happen in the world of organics. So go figure, right? Well, we convert that snake, we convert that dragon over to these types of images that you're seeing on your screen right now. And this is what we would call benzene. And it really does, sometimes we do represent it with multiple double bonds. But we have to understand that a traditional kind of double bond characteristic is not really there. So this is kind of where we started. We understand kind of the conception of this structure at this point. Well, now we condense it down, we shorthand it, and that's what we just did, and we leave off all the hydrogens that are understood to be there. But the problem here is that at this point, no alkene reactions are going to happen like normal. So there's got to be a reason. We think there are double bonds there. Are there really double bonds present? Well, I'll get into that in just a minute. And then over on the right-hand side, you see a space-filling model. So here's our space-filling model. Notice this molecule. It's pretty flat, right? And if you go back and you take a look at some of our rules that we talked about delocalization, we said that these typically happen in flat molecules. And this just so happens to be a pretty flat molecule once we put it into the computer system. Well, all of these carbons are here in the center. There's 6 of them. And all of these hydrogens are around it. It's like a frisbee, folks, right? All these hydrogens are around it. And we're saying that something's happening in this molecule. We think there's double bond, but there's no double bond traditional reaction schemes that are happening with this molecule. So there's got to be a reason. And there's got to be a connection here in order to go from one to the other, because at this point, delocalization was not really a thing, right? Double bonds were okay. Double bond characteristic, double bond reactions, but delocalization, what does that even mean? So what someone decided to do was go into a lab, and they said, okay, let's do this. Let's take benzene. Here we go. Oh, sorry. I got ahead of myself. And we'll do double, single, double, single, double. And what we'll do is that we'll take benzene and we'll replace one of the hydrogens with just another random atom. And it can be something like bromine. And then we're going to do a series of reactions. And if we are correct, this is what will happen. Sometimes this benzene ring has a bromine here. And if we add on a group, bromine could go there. Let's say we add on another bromine. They could go side by side. Or, that wasn't our only option, was it? No, we saw this in various forms. Maybe that bromine could go there. That's different. That's a different molecule than the first one. Or maybe the bromine could go here. That's also a different version of what we had in first and second go around. Or maybe the bromine could go here. And now you're probably thinking, well, wait a minute. Isn't that the same as this? And the answer is no. And here's why. If you look at these two bromines, they are side by side. These two bromines are side by side. They're just on the opposite side. But look in between them. Here we see a double bond between the two bromines, and here we see a single bond in between the bromines. So they really are kind of different. It's not the same structure. So this began to confuse people. Some thought, hey, listen, if we take benzene and we brominate it, and we add on these other groups, we're going to get a mixture of different compounds, and we're going to get a mixture of 4. But time and time and time again, what we saw were only 3 that came from these reactions. How could that be? Clearly, we see there are differences in every one of these. And the reason that number 1 and number 4 are questionable is because they are side by side, but folks, in one version between the bromines, we have a double bond, and in one version between the bromines, we have a single bond. So they are different structures, and they should be represented in a different way. But we only have 3 different versions. Which one doesn't exist? Well, the answer is really none of them. What? None of these actually exist? Not really. No, not really. I mean, yeah, we draw them on a sheet of paper sometimes like this. Yeah, we do benzene with alternating double single bonds like this sometimes. But quite honestly, if we want it to be appropriate, if we want it to be legitimate about it, neither one of these actually do exist. And the whole reason behind all of this confusion is delocalization. Folks, the reason that this benzene does not undergo alkene reactions, it's due to delocalization. Are those double bonds really there? The answer is no, not quite. No, they're not. And then here down below, the reason that we do not get 4 different structures like this is because of delocalization. That's why. Do we really get those types of structures? The answer is no. I mean, they're great to starting out to learn how to do delocalization, but if we wanted to be perfectly honest with each other, neither one of those 4 actually exist. 3 do exist, but none of those. Then what's going on? How should this really be represented? And the answer is over here to the right. That is the true form of benzene. And this circle represents a ring structure, and we could have had a double bond here, or it could move and it could go there, or it could move and it could go here, or it could move and it could go there, and it can move and it can go here, and it can move and it can go there. Folks, we've drawn a dotted line all the way around the ring. So I don't know about you, but I don't want to draw dotted lines like this every time I have to draw benzene. So what they do is that they'll just draw the cyclohexane and they'll just go, there you go. That represents a movement of double bonds. All the double bonds can move in that molecule. Not just one, but all of them. So that is the resonance hybrid of benzene. And that is the truer form of benzene that we see in a laboratory and that we work with and that we should be reading about in literature. So, how do we know this is the case now? Well, here's the thing. 1930s, we get some studies that were done on benzene. And what we found out is that the bond length of benzene was 1.39 angstrom. Do you remember what the measurements were back in lecture module 1 for single bonds and double bonds and triple bonds? Probably not. So let me give them to you. I don't mind. If we have a traditional single bond, it's normally 1.54 angstrom. So this bond length basically tells us, hey, it's not a single bond. If it was a single bond, it would be 1.54. This is much shorter. So they probably are double bonds. Okay, so if you pull the double bond length out from the literature, do you remember what the double bond length was supposed to be? About 1.14 angstrom, give or take a little bit. What? So what we're finding out is that a single bond is longer, a double bond is shorter, but a bond in benzene is 1.39. And I'm going to go back and correct myself. Once again, preempted myself. The bond length that you know for a double bond right now is 1.33, not 1.14. That's something else. Bear with me. All right, so that bond is still shorter than a single, but still longer than a double. So they knew that we actually had a hybrid, right? A mixture of single and double bonds for this. So how on earth can this actually be? Well, this actually started the confusion of there are no really alternating double bonds that are happening here, folks. We're not getting them. There's actually no double bond in there at all, because if there was a double bond there, those double bonds would be 1.33 in length, and they're not. All of those carbon-to-carbon bonds are 1.39. It's not matching. So in some cases it was like a single, in some cases it was like a double, it was a mix, it was a hybrid of both of them. But delocalization is going to explain this. All of this is due to delocalization, or electrons moving throughout the molecule. The whole why the reactions weren't happening, delocalization explains it. The whole why we don't have 4 different kind of products that form from that benzene that's been brominated or substituted, all of that is deal with delocalization. And now this, the bond length, why isn't it matching? All of that is also due to delocalization. Here's another image of benzene. A couple of different images, actually. We start off with benzene. We're not going to be talking about benzene the whole time, but we're starting off with benzene because it was the simplest and it was one of the first that really introduced us to this idea of delocalization and delocalized network. Over here to the left for part A, you see basically the stick structure. And what they're doing is that they're representing these bonds as orbits. So an s orbit from the hydrogen, an sp2 orbital, that creates the overlap. Part B, you're also seeing each one of these carbons have this p overlap, and that's what you're seeing here. That's why the dumbbell shape is there, to let you know that those are available, and those p orbits can be taken up by electrons throughout the molecule. But part C is telling you, listen, you know, we want to look at each one of these carbons, and we want to look at each one of these p's, these dumbbell shapes, individually. But folks, they do overlap. They take up some space. And when they begin to overlap, what happens is that they invade in each other's spaces. That's what goes on. So you actually see this kind of ring, the donut ring, actually form up on top, and then one, of course, on the bottom as well, because the other half of the P is at the bottom of that structure. So we have a very flat molecule, and on top we have this ring that has just morphed all of these p orbits together. And then at the bottom, we see another ring that again has morphed all of those p's together. And then finally, in image D, what you're seeing is an electrostatic potential map there as well. So we've talked about electrostatic potential maps, and we said, hey, everything on the outside that's green, pretty neutral. And then if we go red, that's going to be more of a negative area. And if we go blue, that will be more of a positive area. And what we see here is not truly red. If the electrons were located in one area all the time, then that would peg a little bit redder in color on these structures. But here we see like a yellow-orange color, not truly negative. It's dampened. But this makes benzene very happy. Delocalization makes molecules very happy. Why? Folks, they get rid of their strong negative areas. Delocalization, the movement of electrons, think of people on the run from the cops. Okay, these electrons are not just gypsies now, they're convicts. And they're running. And the more they run, maybe the less chance of them getting caught. Well, these electrons are going to be running. They're going to be moving. They're never going to settle down. And because of that, they don't really root a negative charge in structures. And if they don't root charges, if they don't contribute to a charge, in this case negative with electrons, then these structures, like benzene, are less prone to react, which means it increases the stability. So another rule for delocalization here. If delocalization happens, the molecule loves it. And the reason is because it increases the stability of that molecule. And increasing stability means it typically lowers the reactions that that molecule could experience. Benzene is very stubborn, folks. I can get benzene to do reactions in a laboratory, don't get me wrong. But compared to other alkenes, it is a very stubborn molecule. And the reason it is not really truly an alkene. It is a delocalized network of what was once three alkenes that have come together now and shared their electrons throughout this entire molecule. So no longer is it an alkene. It is something completely different. So I don't want you to get so focused up on benzene that you think that this is the only thing this lecture is going to be about. So I'm going to change gears a little bit, and we're going to do another molecule. And this molecule I'm just going to kind of draw for you, and I'm going to make it look like this. And I'm going to say, listen, Here's a molecule. It's not appropriate. I mean, there's a better way to maybe represent this molecule, but here is a molecule. It's an NO2 at the end, an NO2 group, a nitro group, and it carries some charges. That nitrogen has an extra bond that it normally doesn't have. That's why there's a positive charge there. And that oxygen, it's got an extra set of electrons that it normally doesn't have. So that's why that has a negative. And the oxygen up on top has the traditional two bonds with two sets of electrons. Again, I'm not drawing the dots. They're understood to be there. But the problem here is that that's just the way that I naturally drew it, right? And someone else might come behind me and say, well, no, what if I wanted to do this? And we tell them, that's okay. That's not a problem. But folks, this one doesn't really exist, and this one doesn't really exist. It is a blend of both of these. Benzene did the same thing. Those double bonds don't really exist in a delocalized network. It is kind of a morph between a single and a double bond. So we draw a hybrid, and that was the ring in benzene, and the ring here is not really a true ring. It is a nitrogen that has an oxygen here and an oxygen there, and we said, listen, the double bond could happen here, or the double bond could happen there. And if it does, this might slightly still be negative, this might slightly still be negative, and folks, this slightly might be positive because of that, right? So this is a resonance hybrid. It takes these two forms together, it puts them together into one, and it shows you that it's really a mix between all of these different choices that we have when a molecule is concerned. All right, so that's where I'm going to stop this video. We're going to do more and more examples of these, of course. I mean, we're just now starting. And I haven't even given you the rules for delocalized electrons yet. So how do we know if a set of electrons or if an electron is actually going to be able to move? So that's what we'll learn about in the next video. So come back. That's what we'll talk about. That's what we'll discuss. And I'll let you become more comfortable with this delocalization idea.